Okay, good afternoon, ladies and gentlemen. Moving forward in our chapter 6, of which we are pretty close to being done with, we are going to look at some exponential growth and decay models. And we are going to first look at a little bit of the calculus behind kind of where they come from. But for the most part, we're going to look at the calculus way of doing another kind of integration or solving for y, essentially, called separable differential equations. And we're going to look at these next three, the exponential growth, the exponential decay, and the radioactive decay. Radioactive decay is exponential, but I just kind of like to do it separately. All right, we're going to look at obviously some money problems that we dealt with in pre-calculus. We dealt with some of this stuff in Algebra 2, we dealt with it in pre-calculus, and we're going to deal with it again, but the calculus book likes to describe things obviously a little bit more challenging, but the fact that these equations all come from calculus, or they can come from calculus, they can be derived from calculus or by calculus. All right, on to the first. The first thing we're going to look at is the separable differential equations. And what we're going to start with is a differential equation in this form. dy dx is what ends up being a function of y multiplied by a function of x. We call it separable because we can rearrange this statement to have an f of y and a dy on the same side, and then a g of x and a dx on the same side. What we can do is integrate both sides. Well, if I was to multiply both sides by d of x or dx and divide both sides by f of y, I get this simple statement right here, of which we can integrate. So here is an example. The one example we're going to do is dy dx is equal to xy squared, quantity squared, when y is 1 and x is 1. So we're going to solve for our c value. And so let's just go ahead and go get into this. I have dy dx is equal to what ends up technically being x squared y squared, right? I'm going to multiply both sides by dx and divide by y squared. So I get dy over y squared is equal to x squared dx. What I want to do now is I want to integrate both sides. So I'm going to integrate this. This becomes y to the negative 2 dy. It's a little easier to deal with rather than the fraction. Equals the integral of x squared dx. If I integrate the left-hand side, this becomes negative y to the negative 1 equals x to the third over 3 plus c. Now, normally you would add c to the other side as well, to the y side, but you don't need to because both of the c's will combine together to get a different constant. So we're going to use this constant over here. Now we're going to use our initial value statement. So we're going to say, okay, plug in y equals 1. So I get negative 1 to the negative 1 is just negative 1. And x is 1, so I get 1/3 plus c. If I subtract 1/3 from both sides, I get negative 4/3. So I'm going to substitute that back in. I'm going to say negative y to the negative 1 is equal to x cubed over 3 minus 4/3. Sorry, that was supposed to be a 3 right there. Okay, well, technically, if I can get rid of this negative y, and I can say y to the negative 1 is equal to 4 minus x cubed all over 3. But we can't keep this negative 1 in our problem, so we get y equals, sorry, forgot what I was doing. I am going to reciprocal both sides. So this was 1 over y. This is a fraction here. I can say this now y is equal to the reciprocal of 3 over 4 minus x cubed. And there we go. Pretty cool little problem. And you could verify this for yourself if you wanted to find the derivative of this. Might be kind of challenging for you, but it's doable. Okay, that being said, let's get into, you have a few of these problems like this where you're just going to have to split and take the antiderivative. But a lot of this today is, well, your lesson, your bookwork is going to be word problems. So I know you all just groaned at that, but whatever. That's the way life is in math. All right, so first thing is exponential change. This is how we connect calculus to exponential functions. By solving a simple equation where dy dx is k times y, where k is the growth constant if it's bigger than 0, and decay constant if it's less than 0, we get, through that, what we just did, these separable differential equations, we get a statement saying y is equal to y sub 0 times e to the kt. So k is going to decide if it is a growth or decay, if it's positive or negative. Y sub 0 is obviously our initial value. And initial value meaning like in exponential stuff. So this is saying, this statement right here, that dy dx is equal to ky, just means that y changes at a rate proportional to the amount present. So y being the amount present, dy dx represents change, and when we say proportional to, that just means k times y. And y sub 0 is when time equals 0. Since a lot of this is real world, we're talking about time. So when t is 0, y sub 0 is our initial amount. And remember, we've done this before. We're just kind of defining it a little bit different. So one of the kind of cool things that I've never really mentioned to you guys before is this idea. We've done compound interest and we've done continuous interest, but we've never really connected the two. So if you have invested a sub $0 at a fixed annual interest rate R, compounded k times per year, we get what we might be familiar with, this equation here, where the amount you have at a certain time is equal to the initial amount times 1 plus your rate over the number of times compounded to the power of kt, or k is that number of times and t is the amount in years. Well, here is what's cool about this particular formula. If we were to take the limit of this equation as k approaches infinity, so as k is getting really big here and k is getting really big here, what is really kind of cool is this limits to this equation. Now, some of you might not be familiar with it. You might not remember this equation. That's because in pre-calculus and algebra 2, we call it a PERT. And I just, instead of a sub 0, I used a p to represent principal. Well, a sub 0 is your principal. It's the initial amount that you start with. Okay, so the reason really that I am introducing this one is to kind of show this really cool, the fact that we don't know how to take this limit yet, by the way. Talking about taking the limit as k approaches infinity, it approaches this equation here. But really what I need you guys to get is you need this equation. You kind of need to memorize it. And if you haven't memorized this one yet, I don't know where you've been. We're going to use these through the lesson, not in this particular lesson. I don't think I gave examples for these two types, but you do have them in your text. What I do have examples for are, first of all, HalfLife and how we're going to use equations here. First one, okay, so HalfLife, if you are unfamiliar with it, is the length of time a radioactive material takes to reduce to half its original amount. That's a mouthful. So it's saying if you had 1,000 pounds, so let's look at this carbon-14. The half-life is 5,700 years. Kind of the idea of if you had 1,000 pounds, it will take 5,700 years to get to 500 pounds. So it reduces by half every 5,700 years. So the question that we're going to ask is, we want to find the age of the sample in which 10% of the original material has decayed. So this is kind of a hard question to do because we don't really have, in today's notes, we don't really have an equation for this, but we have a basic understanding of exponential functions. And because we are taking a half every 5,700 years, we can, I'm not saying we can't, but we don't usually use e as a base to our exponential problem. Because we're taking a half, we like to use 1/2 as the base of our exponential function. Well, 1/2 has to go over 5,700 years. So what we do here is we take the time value and divide by 5,700. Because 1 half-life is 5,700 out of 5,700. So if I just want to know what happens after 1 year, I need t divided by 5,700. Now, I kind of put equal signs there. Didn't really explain why. What you would put in front here is the initial amount that you have. Well, you don't know the initial amount, and that's what's kind of cool about these type of equations. It doesn't matter the initial amount. All that matters is what you have left. And if you read this correctly, you want 10% of the original to be decayed, which means you actually have 90% left. And obviously we don't use 90, but you have 0.9 left. And now this really just comes down to you kind of be scared off because you think it's a lot of calculus, but it ends up just being a lot of just write the equation and do some algebra, really. In order to undo exponential problems, let's refresh our memory here. In order to undo an exponential, you must take the logarithm. So I need to take the logarithm, and I will tell you, calculus, like I mentioned last year, will use natural log all the time. Now I'm doing all of the steps here, but eventually you get to the point where you kind of realize you don't need all of these steps. If I take the natural log of a number to an exponent, the exponent comes down to the front. And you're solving for t, so I can, if you think of this as something over 1, so it's natural log over 5,700, I can multiply by 5,700 and divide by the natural log of 1/2, so I get t is equal to 5,700 ln of 0.9 over the ln of 0.5, and I get t is approximately, let's see, where'd my calculator go? I get 5700 ln 0.9 divided by ln 0.5, and I get 800, approximately 866.4 what? I guess we're going years, find the age, so years. And what is interesting about this particular equation, the half-life, and the fact that I used the example from the book talking about carbon-14 is this is used in real-world applications. They use carbon-14 to, or they try to, figure out how long things have been dead, really. Or when was the last time it was on this earth. They do this with dinosaur bones. They determine the amount of carbon-14 in the bones now as to compared to what it should have been, and then they can figure out the amount of years from now, how long ago it was on the earth. But they use this formula. They use half-life to an extent. They use this formula. A slightly different problem here, one that requires a little bit more work, obviously. We have this problem about wasps. I didn't feel like going into the whole part of the word problem in here, but from a population of 10 on May 1st, the number of hornets grow to, I said hornets, but it's supposed to be wasps, grows to 50 in 30 days. If the growth continues to follow the same model, how many days after May 1st will the population reach 100? And this will, if you notice, 10 going to 50 in 30 days means you multiplied by 5 over a span of 30 days, which is going to mean we can use a exponential problem for this, and it's an exponential growth. So here's what we need. We have y equals an initial amount times our growth factor to some exponent. Well, I kind of like to do these problems pretty quick because eventually once you get the hang of this, it actually is pretty quick. So let's get rid of those lines there. And the initial amount that you start with is 10, and you're growing by a factor of 5 every 30 days. So it's the same as the half-life problem. It's going to be t over 30, because in 30 days is when I multiplied by 5. Not after 1 day, not after 2 days, that sort of idea. Now, that's just the equation we get from the basic beginning statement, but we want to know when will it reach 100. So we have 100 equals to 10 times 5 to the t over 30. Don't multiply 10 by 5. Don't do that. Divide both sides by 10. I get 10 equals 5 to the power of t over 30. If I take the natural log of both sides, you can do that whole process again, but you noticed I eventually, on that last page, divided by the natural log of the right-hand side of that natural log of 0.5. So I'm going to do that here. I'm going to say it's now the natural log of 10 over the natural log of 5 is equal to, and again, there's another reason for this, but not really going to worry too much about that. t over 300. Time is equal to 300, not 300. I don't know where the 300 came from. 30. 30. ln of 10 over ln of 5. Do that really quick. Make sure you use your parentheses in every location that's necessary. And you get 42.9. So then you kind of interpret your answer, because maybe this is part of a free response question, and they want to know a very specific statement. So 42.9, what does that mean? Growth rate continues. How many days after will the population reach 100? About 43 days. Not years, not months, but days. All right, pretty simple, not too hard. We've done this for a couple years, always in little sections though. Let's finish off here with what we call Newton's law of cooling. Newton gets his name on a lot of things. It looks like a complex equation, but it's really not too hard. So if T is the temperature of an object at time T, T sub S is the surrounding temperature, and T sub 0 is the initial temperature, whereas time equals 0. Then we get this, like I said, somewhat complex equation. And again, it does come from a kind of a basic exponential or whatever separable differential equation, and this is actually what comes of it. So we can ask this question here. You have a hard-boiled egg, it has a certain temperature, you put it in a pan, typo, pan under running water to cool, not call, C-O-O-L. After 5 minutes, you find the temperature of the egg to be 38 degrees, and how long will it take to reach 20 degrees? Now, this particular problem is going to take 2 different calculations. First calculation is you got to look at this equation and you look at all of the variables. You have 1, 2, 3, 4, 5, 6 variables. Remember, E is not a variable. You have 6 variables. Let's see how many things they gave me. 1, 2, 3, 4, 5. Darn. They actually did not give me enough information to just plug everything in all at once. But let's see what we have. The temperature at time T. So since we're talking about 5 minutes later, we know The temperature at time t is 38. The temperature of the surrounding anything, water, air, whatever, is 18. The initial temperature is 98, minus again that outside temperature, times e to the negative k times 5. Oh, I miscounted, I guess. I have 1, 2, 3, t sub s is one variable. It's 1, 2, 3, 4, 5 variables. They gave me 4 pieces of information, but I can't use that 20 degrees yet. Okay, sorry, my fault. We do some math. This becomes 20 equals 80 e to the negative k times 5. What do you suppose we're going to be looking for? We're going to be looking for k. So if I divide both sides by 80, I get 0.25 equals e to the negative k times 5. Take the natural log of both sides and divide by negative 5. I get k is equal to the natural log of 0.25 divided by negative 5, which is approximately, I did this one already, negative 0. No, sorry, not negative. It's 0.277. Now, if you have that on your calculator, keep it because we're going to use it. All we figured out is what is the k value that represents this particular problem. And you got to remember, k changes for the different problems involved. So you always have to find k, and then you use k to find the question, or find your answer of the actual question. So I have to do that. I have to get that number there. ln of 0.25 divided by negative 5. Okay, now I have it. Now we need to figure out how long. So we need to figure out this t. Will it take to reach the egg to reach 20 degrees? So 20 is the amount of the temperature at time t, minus the surrounding temperature is still 18, equals the initial temperature is still 98, the surrounding temperature is still 18, and now the thing is we have a k value. We have a negative 0.277 t. And the reason it's negative is because the equation is negative. K here was a positive number, so it still remains negative here. And again, we just do some simple math. 2 is equal to 80 e to the negative 0.277 t. Remember that 277 is still on your calculator. And if you follow the process from the left-hand side, we're essentially going to be doing the ln of 1 over 40, or 2 over 80, divided by negative ans, or 0.277. But use the answer key, or the answer button. ln of 1 divided by 40 divided by negative answer, I get approximately 13.3, sorry, not seconds. I don't know why I wrote that. Minutes. Approximately 13 minutes later, it will go to 20 degrees. All right, pretty cool little problem. Again, all based off of calculus, but you notice we didn't do much of the calculus here. We just kind of used the equations. All right, that finishes us off. I will see you guys tomorrow.